We look at this and we see all these squares and we're thinking there has to be something here that has to do with a Pythagorean identity, right? Now, I say that, and then here's two things that come to mind as I look at this. And I'm going to start with this side. I do notice that does factor, right? So if a Pythagorean identity, I'm going to start with the Pythagorean identity because that's usually the most straightforward way to hack at a problem, you know. But if it doesn't work, then maybe I'm going to have to go factor that. But usually I want to try everything I can with a Pythagorean identity first because it usually does make life easier. Now, if you remember, sine squared plus cosine squared was 1. What am I going to do when I've got this expression? Let's kind of mess around with that identity just a minute. I'm just going to make it an x so it's easier to write. This is the identity. Can I get cosine minus sine squared? If I move sine to the other side, it becomes a minus sine squared. But then when I move it back, it's just a plus again, right? It's like you could sit there moving all day long. Nothing's gonna work here. All right. So you might think for a minute that's not, okay, let's throw that idea out of the window and go factor it. But just a second, let's think about this. Look at the second side. What do you see? What kind of stuff's over there? You see a 1. You see some sine squared, right? What if I did this? And this is another kind of thing we haven't done yet, but you might have thought to do to substitute equal values. Since I had my answer over there in terms of sine squared on the right, what if I took cosine squared here and came over to this identity and got it by itself? Because there's some sine squareds over there, and I already got some sine squareds. Maybe let me get rid of the cosine squared. Let's solve the identity over here for cosine squared. Couldn't I subtract sine squared from each side? So maybe I can't substitute for the whole expression, but maybe I can substitute for part of the expression is the idea. Okay, so if I subtract it from each side, here's what I get. I get cosine squared x is equal to 1 minus sine squared. Oh, that's looking pretty good because now I got a 1 that I didn't have before, right? So let me be real clear about what we're going to do here. I'm taking the left-hand side, trying to turn it into the right-hand side, but I am not even going to write that right-hand side down yet. But I saw, from the messing around with the identity over here, that cosine squared is equal to 1 minus sine squared. So I'm going to replace it. I'm going to put it in parentheses just so that I can see that was what I switched out, and I can see I've still got my sine squared. I should put a B on that, right? If you have 1 minus sine squared and you subtract another sine squared, when we collect like terms, wouldn't it be I subtract one thing and then I subtract it again? That's 2 of those things subtracted, It's like that like terms thing. I don't want to make that sign to the 4th B or something like that. This is 1 minus 2 sine squared B just by combining like terms. Oh, I'm done. It might be, oh, look, that's it. I'm finished, and I didn't even know that I was there sometimes. All right. On this one, the thing that always stumped me was I would see a 6 on the left and a 5 on the right. When you see a number go up or down by 1 on an identity, probably you substituted something from a Pythagorean identity, because isn't there usually a 1 in those Pythagorean identities? So that's probably what you're looking at here even before we get started, is that if it goes from 6 down to 5, that's a difference of 1. The Pythagorean identity probably had something to do with that, because we don't have numbers in our identities, do we? Except for those. That's the only place that have numbers. So that's one thing to kind of keep in mind if you see a number change. So let me take the tan squared theta plus 6. And I go, okay, I have some identities. I got a tangent squared on the left, and abracadabra, it turned into secant squared on the right. Let's go look at those identities. If you look at your Pythagorean identities, because they are squares, so we know to kind of go there. Oh my, where's my Pythagorean? Oh, there they are. You got tangent, here's the identity. Tangent squared x plus 1 equals secant squared x. Okay, I know I need to turn tangent into secant. This is going to do it for me, and it's going to allow me to get rid of tangent and introduce a secant. Actually, let me put my equal down here. So I'm going to go, okay, come on. Please take it. Come on. Okay. So tangent squared, over here, if I want to get tangent squared by itself, I could subtract 1 from both sides. Okay, so tangent squared would be secant squared x minus 1. Okay, so I'm going to substitute tangent squared theta with secant squared. I'll just change it to theta instead of x. Minus 1. I'm going to put it in parentheses just so you see that's where it came from. Actually, I'm going to color code it too, and there's my plus 6. Okay, well, secant squared theta minus 1 plus 6 is just secant squared theta plus 5. Oh, we're done already. And all it took was using an identity. And again, when you see these numbers here and you see they're changing, that's probably coming from a Pythagorean identity, since it's the only place where we tend to have ones. You know, everything else seems to be another expression with, you know, another expression with some kind of, you know, trig function in it. Never hurt to have more out here. Okay, so on number 9, that one may seem kind of obvious to some of you guys, but just in case it doesn't, I'm trying to show that if I the left side's equal to the right side, and the right side is cosine squared x. This one's a real straightforward one. If I start with my left side, which remember, I don't ever want to write down both sides and treat it like an equation that I solve. If I multiply this out, so my first step's just going to be, let's multiply this out. This is a Pythagorean theorem kind of thing. This is a plus b, not Pythagorean theorem, it's the difference of two squares. Oh my goodness. And this is a minus b. And when you multiply those things out in math, you get a squared minus b squared. So if I take the a would be a 1, minus the b term would be that sine x, 1 minus sine squared x, that's my a squared minus b squared. Okay. Oops. Okay. But if you think about it, we know that sine squared x plus cosine squared x is 1. And so if I look at 1 minus sine squared x, I can get that to happen over here with my identity just by subtracting sine squared x from each side. Okay, so what I know over here is that cosine squared x is equal to 1 minus sine squared x. Oh, that's exactly what I have over here. I actually did that right. We did that on purpose. This right here is equal to this, so I'll just substitute an equal amount in. Oh, and look, I'm done. All of a sudden I'm finished, and it only took me about, 2-3 steps there.